Good morning, doctor. So this is our report for experiment 4, which is application of first and second law of thermodynamics, and we are from group 3. There are 5 members in this group, me as Towanteng and Elmam, Iman, Henry, and Kong Yongzhe. For introduction is more likely to explain the concept of thermodynamics. So the first one is the zero law of thermodynamics. So we can see from the diagram, if A is equal to C and B is equal to C, then A will equal to B. So this is in the term of temperature. So moving to the second diagram, which is the first law of thermodynamics. So first law of thermodynamics, also known as the law of energy conservation, is stated that energy cannot be created or destroyed. It can only change the form from one form to another form. So moving to the third diagram, which is the second law of thermodynamics. So from the diagram, we can see the heat will flow from the hot reservoir to the cold reservoir. And we see from the explanation, we can't move the heat from a cold object to a hot object without using energy, and also shown that not all the heat can be turned into the useful work. This is because some of the work will be wasted. So if you want to turn the object from the cold object to the hot object, we must use the energy or use the work. The objective for the experiment is to apply the first and second law of thermodynamics in various process. So the scope contains the first one is the fuels are used. The fuel used are limited to milk and coke. So in the experiment, we use milk and coke as our fluids. So the time span used to record the temperature increase or decrease is 1 minute, and the initial temperature range of the fluid is set between the 15 to 17 degrees Celsius.
Next is the theory part. In this experiment, we are applying the first law and the second law of thermodynamics. So the first law says that energy cannot be created or destroyed but changed from one form to another form. So it can be conducted by the equation, the change of E equals to Q minus W, where E is the internal energy, Q is heat transfer, and W is the work done. So the next is the second law of thermodynamics. It says that heat naturally flows from a hotter body to a colder one, and not the other way around if there is no external work. So additionally, there is no process which is 100% efficient. And then for this experiment, the system involved the heat transfer from beaker with hot cola to a cold milk until the thermal equilibrium is achieved. So we can see at the figure beside. So the heat is transferred from the hot cola to the cold milk. Since this is a closed system and there's no motion and no elevation, so there's no net work, no potential energy and kinetic energy. So we can get our energy balance for this system is MC of hot cola times the temperature difference of hot cola equals to MC of cold milk times the change of temperature of the cold milk. So we find that the C, which is specific heat of the cola, is 0.85, and for the cold milk is 3.95.
Alright, for the experimental setup, we have our hot substance, which is our cold substance, which is milk, and we use big beaker for the milk, and we use electrical balance. For our hot substance, we use coke and small beaker, heater, and aluminum foil to reduce the heat loss. We use retort stand for the thermometer, and safety glove for safety, thermometer and thermometer holder.
For methodology, we can see that the first step is we must measure the small beaker by using this electric balance, and the second is measure the big beakers. The third one is when we measure the small beaker and the big beaker, then we record the data in table 1. So after that, we fill the large beaker with the milk until 14 ml, and then we measure the mass of the milk mass. So by using this electric balance, and then we After that, we fill the small beaker with coke until 200 milliliter. Okay, so after fill in the small beaker with the coke with 200 millimeter, and we heat the coke to the 7 degrees Celsius. So while heating the coke, we can cool down the temperature for the milk. And for the experiment, we set the temperature of the milk is 15 degrees Celsius. So after that, we measure the mass of the hot milk, and we measure the mass of the hot coke and the cool milk simultaneously. So we must quickly measure to avoid the heat will lost to the surrounding, and we record the mass in the table one. So after that, we put the hot coke that we'll put the hot coke with 70 degrees Celsius into the cold milk. So in the last bigger one is the cool milk, and the small bigger one is the hot cola. So after that, we measure the initial temperature of the hot coke and the cold milk. So after putting the small beaker into the big beakers, and we set two temperature to measure the initial set two thermometer to measure the initial temperature. So after put the hot coke and the cold milk together, and we set that the two thermometer to measure the initial temperature, and we record the initial temperature in the table two. After that, we start the stopwatch 1 minute. After 1 minute, we record the readings of the temperatures in table two. So after record the reading two, and then we repeat the step. We repeat until the hot coke and the cold milk are the temperature are same, which is in equilibrium. So after that, we calculate the change in the temperature and the heat loss, and then we plot the graph.
And then for the result, this one is the table one. It is the data for the small and large beaker. So we record the mass of the small beaker and big beaker, and followed by which is filled by hot cola and cold milk. So we can get our mass of the hot cola and the cold milk. Secondly, this is table 2. It is the table of temperature of hot cola and the cold milk with time. So we record the temperature of hot cola and the cold milk every 1 minute until it reaches the thermal equilibrium, which is at 13, 14, and 15. After that, this is table 3. It is the table of energy change of hot cola and cold milk with times. So from table 2, we can calculate our temperature change of hot cola and also the cold milk. So record here, then we can use this data and the formula at the below to calculate our heat loss, which is MC times the change of temperature. So by using the specific heat as shown below, we can calculate our total heat change is equals to 4.1165, and the total heat loss to the surroundings is 0.7370239.736.
So as for the discussion, the discussion stated that discuss your observation during the experiment conducted and relate them with changes in energy, the first and second law of thermodynamics. Your discussion must be supported by all related graph and calculation. So as for the calculation, we will calculate the mass of the hot coke and also the cold milk used by subtracting its own mass of beaker. So for hot coke it's 0.036 kg, and also the cold milk it's 0.202 kg. And with the sample calculation of by calculating its change of energy, so we use the equation equals to m specific heat capacity mass multiplied by heat capacity specific heat capacity, and so the temperature change by the hot coke. So yeah, and that's the uh, way of doing it. We get negative 1.4688 kilojoule, which is the energy release. While the cold milk, we will get 5.5853 kilojoule, which is the energy absorbed. And with the total energy change, we use the formula of energy in, energy out, minus energy out equals to energy system. And we will get the 4.1165 kilojoule. And also with the percentage of energy loss to the surrounding, we divide by the total energy change in the system by the cold milk, which is the energy absorbed, multiplied by the 100%. So we get 73.7% of the energy loss to the surrounding. As for the to explain the situation from the discussion, based on our calculation and also result, for the first law, total energy lost by hot cola is not equals to energy gain by the cold milk exactly due to the heat loss to the environment. From the table, final net energy transfer, where heat lost by cola plus the heat gained by milk, it's my negative 1.4688 plus by the 5.5853 equals to 4.1165 kilojoule, which I shown the calculation previous slide, and but only 3.3795 kilojoule, which example it's 4.1665 minus by the 0.7373 70 was truly exchanged between the two fluids. This thus the remainder was lost to the surroundings. It proved that the remainder is already lost to the surroundings for the heat. And this confirms the first law, accounting for energy conservation across the system plus surrounding. To explain for the second law with the proof of calculation. Second law of thermodynamics, which is the entropy increase, where heat flows spontaneously from a hot body to a cold one, increasing the overall entropy. Where the hot cola cools down, decrease in temperature, thus decrease in internal energy when the cola is inserted wi- into the milk, and cold milk warms up, increase the temperature and internal energy as well. The direction of heat transfer is one way from hot to cold and irreversibly, and also some heat is lost to the surrounding, which increases the entropy of the universe. This aligns with the second law, as the process shows an increase in disordered entropy due to the energy dissipation. To explain our graph above, the temperature of hot cola and cold milk versus time. As you can see from the graph, the temperature of hot cola, which is the blue line, started from a very high temperature of 70 degrees Celsius, going down decreases the temperature, uh, and also the temperature of cold milk increases together, which aligns at the end of the several minutes, at the end to 50 minutes time, and it aligns, which shows that it is at thermal equilibrium. Due to the first law of thermodynamics, energy is conserved as heat flow from hot to cool. The second law is shown by the heat moving spontaneously from hot to cool, and with the transfer flowing as temperature equalize, which is the thermal equilibrium have achieved. To further explain the graph shown, the hot cola temperature decreased while the cool milk temperature increased due to the heat transfer from hot to cool. Although the theory suggests that the total energy change should be zero, but from our calculation show 4.1165 kilojoule change. This difference is likely due to the experimental error, such as the uneven heating from not stirring the water at all times, heat loss to the surroundings, and also the parallax error when reading the thermometer. To improve the accuracy, the water should be stirred at all times while during the experiment. The thermometer readings should be taken at eye level, 90 degree, to avoid parallax error, and also the experimental should be done in a closed draft-free area.
Okay, for the conclusion of this experiment, it shows how the first and second laws of thermodynamics work in real life. The first law was proven because the heat lost by the hot cola was almost equal to heat gain by the cold milk, showing that energy was not lost, just transferred. The second law was also shown clearly. Heat moves naturally from the hot cola to the cold milk until both reach the same temperature. This is how heat always flows from hot to cold without needing extra energy. Some heat was lost to the surrounding, which explains why the energy transfer wasn't perfectly balanced. Things like not stirring the fluid or reading the thermometer incorrectly may have also occurred small errors. In the end, the experiment helped us understand how energy moves and changes, and why heat always spreads out unless something forces it not to.
Safety procedures. We can divide it into two parts, which are equipment handling and measurement accuracy. For equipment handling, first, handling hot equipment. We can use heat-resistant glove when handling hot beakers to prevent burns. Second, to prevent heat loss, we can use aluminium foil around the beakers to reduce heat loss during the observation period. And then the last one is monitor heating process. Never leave the boiling process unattended and turn off the heater immediately after use to avoid overheating. And then for measurement accuracy, first, handling the thermometer. We need to place the thermometer securely and vertically in the fluid material used and make sure the bulb is fully submerged but not touching the beaker wall or bottom. This is to get the accurate readings. For doing this, we can use the thermometer holder or retort stand. And then second is parallax error. To avoid this, we can place a white paper behind thermometer to get accurate readings. And then the last one is data accuracy. We need to take 3 readings of each data, which is beaker weight and temperature, and calculate the average to get more accurate reading. These are the references we use to make this report. All of them are from their internets, and that's all from us. Thank you.